So welcome everyone, and thank you for joining this evening lecture of Young Second. As there are a few people who joined after the AGM, I have to repeat a few housekeeping rules. There is no fire alarm drill planned for tonight, so if you hear the fire alarm, please evacuate the room from one of the two doors and get out of the main building and turn left and left again into storage gates. Mobile phones, if you could make sure that your mobile phone is on silent mode, it would be very much appreciated. Tonight we have invited Mohamed El-Zeadani, a PhD student at Imperial College London, to give insights from his recent experimental study on cyclic response of rubberized alkali-activated concrete fill steel tubes. This work was funded by the Second Fund 2022. And Mohamed's PhD research is focused on the mechanical and structural behavior of rubberized alkali-activated concrete, including the material characterization and structural response under cyclic loading conditions. His technical interests involve developments in sustainable concrete materials, numerical modeling, and mechanics-based solutions for concrete structures under various loading conditions. And Mohamed is also an elected member of the second Young Members Subcommittee. So let me just remind you that after the talk, you're all invited to the networking drinks in the IC bar, and one free drink is provided by Second. So without further delay, I will hand over Mohamed for tonight's evening talk.
Thank you very much, Marco. It's indeed a great pleasure to talk to you today a bit about my PhD research, mainly on the cyclic response of steel tubes infilled with rubberized alkali-activated concrete. So this is really what I'll be presenting to you about today. We tested some steel tubes under reverse cyclic loading, and we looked at the member response and other key seismic design parameters. But before I talk about this, it's perhaps wise just to let you know how we got to this point, what is alkali-activated concrete and what rubber has to do with it. So you might be aware that concrete is the most consumed material on the planet, second actually after water, and we produce about 30 billion tons of concrete every year. And this is a very large number that is sometimes hard to imagine. So just to put it in perspective, at this rate we produce enough concrete to fill the size of Big Ben every 35 seconds. In other words, we produce enough concrete to fill the size of over 900,000 Big Bens in a year. That's a problem because cement, one of the main ingredients in concrete, its production is quite highly energy intensive and is responsible for about 8% of global carbon emissions. So if cement was a country, it would be ranked third, just behind China and the US, and way ahead of the UK in terms of carbon emissions. So conventional concrete at its most basic level is made up of cement, sand, gravel, and water. And alkali-activated concrete tries to avoid cement completely. It replaces that with industrial waste materials. The most famous among those is blast furnace slag and fly ash, and these are less reactive than cement. So usually a chemical activator is added to the mix just to enhance the reaction of those industrial waste materials. And then you have the sand, the gravel, and the water, just like in normal concrete. And in case you're wondering, fly ash is a byproduct of burning coal in electricity generating power plants, and blast furnace slag is a byproduct of iron manufacturing. Then rubberized concrete is basically replacing a proportion of the natural aggregates, including the sand and gravel, with rubber particles derived from end-of-life tires. And end-of-life tires are notoriously difficult to recycle. Every year, about 1.2 billion tires reach their end of life. A lot of them get discarded in landfills. So the possibility of using them in concrete is indeed promising, but not just from a sustainability point of view. Adding rubber into concrete changes its behavior. It makes it more flexible so it can be used in certain seismic applications. It increases the ductility of the concrete. So these are the constituent materials that I've used in my PhD research. So the cement replacements include the fly ash, blast furnace slag, and a chemical activator. In my case, I've used sodium metasilicate anhydrous. And then we added another chemical called borax just to enhance the workability of the mix and increase the setting time for this type of concrete. Then there was the sand gravel, and we used 6 different sizes of rubber particles just to ensure an optimum gradation of rubber. And then we initially tested 5 different mixes. We named them R0, R15, R30 up to R60, and this just refers to the rubber replacement ratio. So R0 had no rubber content, and then R15 is we replaced 15% of the natural aggregates with rubber particles, and so on until R60, which had the largest rubber replacement ratio of about 60% of the natural aggregates. So this is the preparation process. I mean, quite similar to normal concrete, mixing the dry ingredients. So I did this in the lab for about 5 to 8 minutes, and then adding water and mixing for another 5 to 8 minutes, and then casting and allowing the specimens to cure. So we cure them under ambient laboratory conditions. This is just a photo, a cross-section of one of the cylinders, the R60, with the R60 concrete having the largest rubber content. Just shows the dispersion of rubber throughout the cross-section. Then we initially tested those for the fundamental mechanical properties, including the compressive strength, the stress-strain response, the splitting tensile strength, and the flexural strength. And these are the results for the compressive strength. So on the y-axis, I'm plotting FC, the compressive strength in megapascals, against rho VR, which is the rubber replacement ratio in percentage. And these are the results for the cube and cylinder compressive strength. And as the rubber content in the mix increases, the compressive strength reduces, which makes total sense. Rubber is weaker than natural aggregates, and the more you have of it in your concrete, the weaker it becomes. But then these are the failure patterns. So the non-rubberized one, the R0 specimens, they kind of failed in a very brittle manner, whereas the ones with the rubberized concrete, I'm showing here R30 and R60, they kind of failed in a gradual manner by sliding across a diagonal crack. Then these are other mechanical properties, including the elastic modulus, splitting tensile strength, and the flexural strength. Plotted against the rubber content, and they follow the same trend we see for the compressive strength, and that's the more rubber you have, the lower the mechanical properties we see. But then when we look at things like ductility, for instance, which we got from the stress-strain response as the ratio of the strain corresponding to about 85% of the compressive strength on the descending branch to the strain corresponding to about 65% of the compressive strength on the ascending branch, we see as the rubber content increases, the ductility of the concrete increases. And we see the same when we look at the normalized crushing energy. So this is again was determined from the stress-strain response by the shaded area shown there as GC. And just to allow non-dimensional comparisons, we divided that by the compressive strength. And as the rubber content in the concrete increases, we see an increase in the normalized crushing energy. Then we went further, we tested those under cyclic compression. So I'm plotting here the stress-strain response for R0, R30, and R60 specimens. And the R0 ones, they kind of failed immediately after reaching the peak compressive strength, whereas the ones with the rubber content, they kind of showed a very nice post-peak cyclic degradation behavior. And then we did we studied the impact response of such concrete under compression and splitting tension. And we were mainly interested in the dynamic increase factor. So this is simply the ratio of the dynamic strength over the quasi-static strength at a given strain rate. So I'm plotting here the results for R0, R30, and R60. And the dynamic increase factor tends to increase as the strain rate increases, initially gradually, and then there comes a point where it just shoots up. We call this the critical transition strain rate. What's more interesting is I'm plotting in the red lines the predictions by the CEB Model Code 2010, and as the rubber content in the concrete increases, the expressions kind of become inappropriate for rubberized concrete. We see that for under compression, and the same here for splitting tension. And we just see that the rubber really dominates or controls the behavior under impact. So up to this point, we're like, okay, we fairly understand now the mechanical properties of rubberized concrete. Now, is there a way to reduce the strength loss due to rubber addition and maintain the deformation benefits we see from rubberized concrete? And that kind of led us to look at confinement. So we looked at concrete-filled steel tubes, circular sections and square sections, and we looked at another system of confinement by wrapping of our specimens with fiber reinforced polymer. So I'm showing here the failure patterns for the FRP confined specimens, that they failed by rupture of the FRP and crushing of the concrete. And these are the failure patterns for the concrete-filled steel tubes. They failed by, as you'd expect, buckling of the steel and crushing of the concrete. So these were tested under axial compression. And this just shows here the comparison of these. Also on the left side, I'm plotting the axial strength against the rubber content. So the bottom line is the unconfined strength, and just shows how having one layer of FRP confinement, how that increases the strength up to having 3 layers, which shows quite decent strength even for the specimens with the highest rubber content. And then the plot on the right here shows for the concrete-filled steel tubes, just shows the effect of the steel on the strength. So there's the square specimens and also the circular specimens. We actually went further and we did some numerical modeling just to really understand the effect of confinement. We considered, so here I'm plotting the confinement effectiveness, which is simply the confined strength over the unconfined compressive strength, against the confinement ratio, which is a function of the FRP material properties. And we see kind of a linear relationship between the two, which is just saying that the more confinement you have, the higher the strength. And this is not affected that much by the type of FRP. We considered glass fiber, aramid, carbon fiber reinforced polymer, and basalt fiber reinforced polymer. And we did the same as well for the concrete-filled steel tubes. Here I'm showing the results for the circular sections. We compared the axial capacity prediction equations in Eurocode 4 and as well as the American code. So on the x-axis I'm plotting the experimental results, or the finite element modeling results, the axial capacity against the modified code equations. We had to modify the code equations just to account for the effect of rubber on confinement and to get good accuracy of the results. So it was, at this point, we're like, okay, we understand very well the axial behavior. What about the member cyclic response? And then this was around last year, and then the second fund came through, so that kind of encouraged us to really look at the member cyclic response. We decided to look at square steel tubes infilled with rubberized alkali-activated concrete, mainly because of limitation. We couldn't test circular sections because of time and money-wise. And then there are a few studies in the literature that looked at the effect of rubberized concrete on circular sections. And these members are widely used in practice, so we figured we might study them and really understand how rubberized concrete affects those square tubes. So the specimen details for this particular experimental program, we tested 9 different specimens. We kind of grouped them into 4 groups. So the initial 2, the ST there, ST stands for steel tubes. These are just hollow steel specimens for comparison purposes. And then the CF stands for concrete filled, and then the type of concrete infill. So we considered R0 mixes, R30 and R60. All specimens were 100 times 100 millimeter in cross section, and they had a nominal length of about 1,200 millimeters and a steel tube thickness of about 2.8 millimeters. And then we considered 2 axial load levels, about 0, which represents a case under bending, and 20% of the axial cross-sectional capacity. And these are referred to as N0 and N20 in the naming format. For the R30 specimens, we had an extra specimen, so we decided to test it under an axial load level about 10%. And then for the test setup, so we welded steel plates at the top and bottom of the specimen, and then we bolted the bottom plate to a very stiff foundation, so that the specimens were essentially tested as vertical cantilevers. And then we had a vertical actuator that applied the axial load, which was maintained throughout the test, and then a lateral actuator that applied the lateral displacements. And this is the displacement sequence. So initially, before yield, we applied 1 incremental displacement up to about a displacement level of 12 millimeters, and then we applied 3 repetitive displacements that increased up to about a drift ratio of 10%, or but 120 millimeter displacement on each side. And these are just the material properties. So the infill concrete, these are the stress, strain curves and strengths for the infill concrete. So the R0 specimens had a 28-day strength of about 72 megapascals. The R30 concrete was just over 20 megapascal in strength, and the R60 concrete was about 10 megapascals. Then these are the properties for the steel tubes. We did coupon tests. Because of the working of these square sections, the corners, residual stresses tend to develop in the corners, so that increases the yield strength. So we did tensile coupon tests from the flat sides of the tube and from the corner sides, and these are the results. And then we did some squash tests, which kind of gives a more representative value of the cross-sectional capacity. And we took the yield strength to be that, which was about 295 megapascals. And then these are the results. So I'm plotting here the moment against displacement response. So the moment what I'm plotting here is the base moment, the largest moment experienced by the member. And the displacement is the displacement at the top of the column. This is the horizontal displacement. And then I'm also plotting at the bottom there the lateral load against the displacement results. And the lateral load was taken as the effective lateral load at the top of the member, plotted against the top displacement. So these are the results for the hollow steel tubes. N0 is the zero axial load level, and N20 is when they had an axial load level about 20% of the cross-section capacity. And then these are the results for the R0 infilled specimens. And these are for the R30. I'll discuss them more in a bit. And these are the results for the R60 specimens. A good way to compare them is to look at the backbone curves. So these are the results for the backbone curves, including the moments and the lateral loads for a given axial load level. And I'm going to discuss those further, but I'll show you the failure patterns. So the hollow steel tubes kind of failed by inward and outward buckling, and then they develop fractures at a given displacement rate. Whereas the concrete-filled steel tubes, they all fail by outward buckling and crushing of the concrete. And then at about drift ratios of 10%, they started to develop fractures at the buckling area. So these are the ones for the R30 infilled tubes and R60 infilled tubes. Here we looked at the member stiffness. We took this as the second stiffness, which is basically plotting a straight line from the origin to about 40% of the peak lateral load. So we took those from the lateral load displacement envelope curves. And one thing we noticed, so these are the results for the specimen with zero axial load level. So as the rubber content increased, the second stiffness reduced. And that makes sense because the rubberized concrete has a lower elastic modulus, so you'd expect to see that. And then for a given member type, we noticed that as the axial load level increased, we saw a reduction in the second stiffness. That was quite significant in certain members, indicating that the second stiffness was sensitive to the axial load level. Then we looked at the moment at first yield, also from the envelope curves of the moment displacement curves. And this was estimated as the straight line from the second stiffness coinciding with the horizontal line at the peak moment, and just plotting an arrow down to get the estimated moment at first yield. And then these are the results for different specimens. So one thing we noticed for the concrete filled specimens is that as the axial load level increased, we saw that the moment at first yield increased across all concrete filled specimens, but as the rubber content in the concrete infill increased, then the yield, the moment at first yield reduced slightly. The same thing with the peak moment. So at least for the axial load levels considered in the study, we saw that the peak moment increased as the axial load level increased, and then as the rubber content in the concrete infill increased, the peak moment reduced. However, this reduction is far less than what we see from the unconfined specimens, just when I showed you earlier the compressive stress strain responses. And this is mainly due to the steel contribution 1 and also the members here are subjected to bending as well, not just compression, as in the case of the unconfined compressive strength results. And then we looked at the ductility. So this was taken as the ratio of the ultimate displacement to the yield displacement. And the ultimate case here was taken as a drop in moment about 15% from the peak moment. And then we noticed that as the axial load level increased, the ductility in the members reduced, which makes sense. But then we noticed that as the rubber content in the concrete increased, the ductility still reduced, indicating that those square tubes didn't really benefit that much from the rubberized concrete infill, unlike what is commonly reported for circular sections infilled with rubberized concrete. And we do think that this is mainly because of the lower confinement that the square tube, the section, imparts on the infill concrete. Then we looked at the strength interaction. So we looked at Eurocode 4 provisions for a member subjected to unaxial bending with a coexistent axial load. And we noticed that the test results here fall outside the Eurocode 4 axial load moment interaction curves, indicating that the code is quite safe for such members, in fact, a bit conservative. And then we looked at the plastic hinge length as well. And while testing, we had cameras here that kind of monitored the displacements near the fixed end of the column. And then I post-processed the results and then placed virtual strain gauges on the area of interest, placed about 35 virtual strain gauges, and then looked at the axial displacements at a given displacement level. So here I'm just plotting some of the results for the concrete filled specimens at 0% axial load, which clearly shows, I'm plotting this across the height and then the strains at a given displacement level, and it clearly shows where the inelastic strains develop in the member, and that's basically the plastic hinge length. So this is a summary of the results. So we notice a similar trend. So that's as the axial load level on the specimens increases, the plastic hinge length reduces. And another thing is, as the rubber content in the concrete infill increases, the plastic hinge length reduces slightly. Then last but not least, we looked at the energy dissipation. So this was taken by the area under a full cycle. And just to make non-dimensional comparisons, we divided that by the peak moment, and then we plotted the results against the displacement level of that cycle. So these are the results for the R0 specimens. So the black solid line is the energy dissipation from the first loop, and then the first cycle at a given displacement level, and the red line is the energy dissipation from the third cycle, which just shows here the degradation in the material. So these are the results on the left for the specimens subjected to a 0 axial load level, and on the right for subject to about 20% axial load level. And for convenience, I'm plotting those results. The dashed lines are the results for the hollow steel tube, just to show comparisons and show how the concrete infill helps a lot with the energy dissipation. So these are the results for R0. These are the results for the R30 infilled steel tubes and R60. And really, we don't see much of a difference. When you look at the normalized energy dissipation, we don't see much of a difference between the concrete filled specimens. However, as the axial load level increases, we see a reduction in the normalized energy dissipation. So to finish this off, so as the rubber content in the concrete infill increases, at least for the case of the square steel tubes, we do see a reduction in stiffness peak moment, which was expected from the beginning. But the other thing we did not expect is a reduction in ductility and plastic hinge length, indicating that really the rubberized concrete didn't help that much for the case of the concrete filled specimens. And then for the axial load levels considered in this study, so reduction in stiffness, ductility, plastic hinge length, and energy dissipation, and an increase in moment at first yield and peak moment. Perhaps on a positive note, just comparing the results of the R60 infill specimens with the hollow steel tubes. I mean, although the rubberized concrete didn't really help that much, but when you compare it to the hollow steel tubes, you see an increase in almost all parameters, more significantly the ductility. And before I leave you, just a few thank yous to the SECIT Fund. I think around this time last year when we were starting out, I was running out of funding on my scholarships, so the money that came from SECIT did indeed help, so thank you very much. I'd like to give thanks to my supervisors for the many fruitful discussions, from deciding what to test during testing and discussions after testing. And last but not least, I'd like to thank the technical staff at the Structures Laboratory, in particular Trevor and Susanna. I see Susanna here. Really, without them, I wouldn't be able to do these tests in the lab, so thank you a lot to them. Particular Trevor, who would sometimes stay with me a bit late until 6-7 p.m. to finish the test of the members. I have a photo of Trevor here looking at the specimens, just seeing if a fracture has developed so that we could stop the test and go back. So thank you very much, and that's all for me. I hope you find this presentation insightful.
Many thanks, Mohamed, for the brilliant presentation, and I'm sure that the audience here and online have enjoyed your experimental work and your journey that was also supported by SECIT. So we can open up the room for questions. There are no, at the moment, questions online, so I'm going probably around with the mic, and if you have any questions.
Hey, thanks for the presentation. I'm Swanan Patil, structure engineer at COVI. First one is a little bit counterintuitive. Have you thought about reinforcing the, like instead of having confinement from outside, just more traditional way to do is to...
So in my PhD research, I haven't done any on that, but we have some in our group a few years back who looked at normal reinforced concrete columns, and they looked at the cyclic response using rubberized concrete as well, yeah.
All right, and then little bit, I think it is a comment rather than a question. I attended a Syria discussion around prediction versus precision and all about these new materials being used for sustainability. And there was one representative from an insurance company, civil engineer working in insurance company, and their view at these topics, I was also shocked that when they see any new material being used in a structure, they kind of downgrade the level, and that's a new kind of discovery. We are trying to go in one direction, which is very important. But then, how have you thought about, or is there any thought to lead any discussion that direction?
Yeah, I know the insurance people. They're usually very conservative and very safe. So they haven't seen these materials used in practice, so they naturally downgrade them. Personally, I haven't looked at any, to be honest. I just mainly focused on my PhD research. But it's an interesting point to keep in mind.
We've got a question from our online audience. Nihal Menezes from Sheffield, the University of Sheffield, is asking whether, in terms of earthquake protection, what's the best solution for energy absorption among those that you mentioned? Steel tubes, filled, or carbon fiber filled tubes of rubber alkalized concrete?
So I haven't done any testing on cyclic testing on FRP kind of reinforced or external confinement, but we have a colleague in our group who did some tests on circular steel tubes infilled with rubberized concrete, and she does see an increase in ductility and energy dissipation with an increase in rubber content up to a certain point. So these are definitely, they have a better performance compared to the square steel tubes. There are some studies in the literature that report the effect of FRP confinement when in cyclic loading, and they also seem to report that there is benefits in ductility. You get more longitudinal strains that develop in reinforcement in the case of columns and so on. So that's useful as well. But comparing the two, I really can't make an answer now which one is better. But both do enhance the ductility energy dissipation for such columns.
Mm-hmm. Thank you. Questions from the audience? Okay.
Hi, my name is Vansiti Rao. So my question is, before you are going to test, have you done any slump test or something like normal?
Yes.
For normal concrete, we do the slump test before proceed for the further mechanical behavior. For the rubberized concrete, how you fix the slump test? Like how we adjust the slump test?
That's a very good question. So initially, while optimizing the material, so this was the first thing that I did when I came for my PhD, is trying to optimize the material. We had two targets: high compressive strength, because we were expecting when we add rubber, we're going to lose some of that strength, and high workability. And we were targeting something above a slump of above 150 millimeters. So because when you add rubber, the slump reduces. And then we eventually got something around 200 millimeters, which is a very high slump. And as you add rubber, the highest, so the R60 specimens had a slump of around 150. And the reason we were targeting high slump is because we were thinking when we get to the structural level, when you have reinforcement and all of that, so if the concrete doesn't flow well, then you're just not going to spread well, and you're going to have problems while placing it. So yes, to answer your questions, we looked at the slump, and for the highest rubber content, it was around 150 millimeters.
Okay, regarding the slump test only, that addition to that same question. So when you prepare the concrete, you will see cement water aggregate ratio. So for the rubberized, so you consider it as a aggregate.
The rubber was considered as aggregates, yes.
Okay, thank you.
Perhaps an observation rather than a question. Ian Smith from Atkins. The question before last was about carbon fibre, but carbon fibre is brittle. It's got phenomenal strength, but it's brittle. I think what you chose, really, steel and rubber, seem to have a compatibility in the ductility, maintaining a stress level in steel for a considerable ductility, and the rubber providing the complementary bit to keep the tube in good order. So with the fibres you were looking at, what was the range of fibres that you were looking at?
The range in terms of...
in different materials.
So the experimental study we did was on exile testing, and we looked at aramid fibre reinforced polymer. It had an elastic modulus of about 100 gigapascal.
Yeah, so that's, again, whilst it's not ductile, it's actually got a nice modulus, hasn't it?
Yes.
Whereas carbon fibre, again, tends to be high modulus.
And then we did a numerical study where we kind of initially validated the model against the experimental results, and then we varied the elastic modulus of the fibre from as low as 60, which represents the case of basalt and glass, up to about 150, which is the case for carbon, and it could go even higher. But the thing is, if you look at the stress strain response, because as you said, it's brittle, you stretch it and then it just snaps. The stress strain response is quite interesting. It goes up, it's like a bilinear curve, and it does enhance the ductility, deformation characteristics, and so on. So we saw that under exile testing, and the studies in the literature say that it does help as well when cases of cyclic loading and so on. So it is useful. But the reason actually we went with concrete filled steel tubes, because new members, this could be used for new members, but FRP is usually used for retrofitting applications. So that's one thing that made us go for concrete filled steel tubes.
Good, and the takeaway for me then, concrete filled tubes have got the compatibility there. That seems to be an optimum balance.
That's another thing as well, yes. Yeah.
Thank you very much. Colin, you must have some questions,
Hi, Fabio Freddi, UCL. Thanks a lot for the presentation, very interesting and very comprehensive work, starting from the characterization of the material to the test, very interesting. So I have two questions. So you show that there is a reduction of the crushing so the ultimate strength of the concrete. So I was wondering about the cracking strength, because of course I would expect that will be a bit higher with respect to conventional concrete, and that will be a big advantage, I think, for you have a lower reduction of the stiffness of the material. That will be a significant advantage for also for seismic applications. This is the first question. The second question is, what about the long-term performance of these systems? Because the rubber, I'm not an expert, but I would expect it as an evolution with time, while the conventional aggregates they shouldn't have it. So I don't know if you have any comment about that.
A very good question. So we did a creep test, just placing some sustained load on our specimens for 1 year, and we saw that the creep coefficient is higher for the rubberized concrete compared to the non-rubberized concrete, mainly because rubber is softer. We think that at the interfacial transition zone between the rubber and the cement matrix, it's weaker, so that contributes to higher creep and so on. So that's part of the reason we started going into kind of composite sections, where the creep doesn't become as critical as for, let's say, fully concrete sections. So we do see that in terms of degradation of rubber and of that comes under the durability side of things. So I didn't do anything in my PhD with that regards. For your first question, the cracking strength.
Yes. So you show that there is a reduction of the crushing, so the ultimate strength of the concrete.
Yes.
So I was wondering, what about the cracking strength? So the
cracking strength here, what do you mean by it? Is it?
So let's talk about tensile strength instead of talking about compressive strength.
So one thing we looked at is when we tested those prisms, we looked at the crack width. The flexure strength reduces as the rubber content increases, but the crack opening becomes quite gradual and larger than what you would see for non-rubberized concrete. So definitely you get a huge kind of cracking energy dissipation compared to the non-rubberized concrete. Yeah.
Okay. Thanks a lot.
Thank you for the presentation. This was very, very nice. Raffaele De Risi from University of Bristol. I have just a few curiosity about this very comprehensive experimental campaign, and also a question about usability in a very specific situation. So first of all, I was just curious about the kind of damage you observed at base, if that local buckling is always the same typology, or there are different typology, or if you observe also different kind of failures. Second is most a curiosity, what do you do with the base plate? You just throw it away or you reuse it when you do your experiment? Just, thinking about money. And the third thing is, have you thought about the situation of fire resistance of this material? Because obviously having rubber, you may have some implication, right?
Okay, so I'll start backwards because that's how I remember them. So the fire properties, we wanted to do some fire tests. We wanted to put rubberized specimens in the oven and then see the residual compressive strength and all of that. But then we need to go through a lot of safety things that we eventually decided not to do, because you get fumes that come out of the rubber. So we decided not to do it. But then there are a few studies in the literature that says, because when you add rubber, the concrete becomes more porous, so it has a higher residual compressive strength than the non-rubberized concrete. But then again, the fumes and all of that is an issue, and that's why actually having concrete filled steel tubes is actually quite useful in terms of fire of such materials and so on. Your second question was the plates. Yeah. So actually the plates we used on this one were recycled. And I think hopefully the specimens are still in the lab. We plan to open them up and look at the crushed concrete, and hopefully we'll recycle them for a next experiment. And I really forgot your first question.
Local buckling of days, if that is always the same, or you observe different kind of failures.
So that's the. I haven't got to that part yet, but I would look at the development of local buckling. When does it initiate, and so on. And also the fracture development in those specimens. So that it's still an ongoing study. I also have to do some numerical modeling. That will keep me busy for my last year of my PhD. But hopefully it will be published at some point.
There are two more questions from our online audience. One is about costs. Is it like an expensive solution, or somehow it can be made cheaper in the long term?
So cost-wise, it is a bit more expensive, mainly because of the chemicals we use. I mean, the sodium, this chemical activator we use is slightly more expensive. So if you compare directly, alkali-activated concrete is slightly more expensive. I don't know if it's going to get cheaper, and if the production increases, then it becomes cheaper. That's something else.
And the second question is from the same person that asked you about what was the best solution. He's asking whether using a different steel alloy would, for the tube, that is more ductile and stronger, would probably be a solution to improve this, or you don't see that as a...
I mean, it's definitely, if you use a more ductile alloy, it will increase. But then what's the point? If you're having already a more ductile alloy, you don't need rubberized concrete. I would say have high strength steel with lower ductility and have rubberized concrete in it is better than having a more ductile alloy.
Yeah. Other questions from our audience here in London? Please, Ian.
It's Ian Smith again from Atkins. I forgot to thank you for an excellent presentation. My last question. Another observation from the gentleman about the creep of the material. By the time, putting ordinary concrete filled tubes, the concrete creeps anyway. So you're usually looking at the steel, but the benefit of filling it is the advantage. So I think that's important.
Yes.
And also in terms of developing its properties. Presumably when you're building a building, you can design the building on the steel tube alone in terms of construction. Really, the rubber's going to come in and play its part many years later, probably, when it's seismically challenged. So I think there's a lot of comparability in the way you've mixed two materials. And the beneficial thing is you're actually isolating a whole load of rubber, which would just, as you said at the beginning, be just landfill. So yes, I think it's good.
If I were to comment on this, you hit the nail on its head. Yeah, that's exactly what it's supposed to. I mean, the whole research is for those kind of applications, to kind of use rubber, add some ductility, or if you get seismic loading, then it becomes useful and so on. And as you said, the steel could be designed to carry the gravity loads.
Yeah. And
then the rubber could eventually support with when you get lateral loading.
Yeah. Thank you very much. Excellent evening. Thank you.
Thank you, Ian. And maybe one question from me, just to conclude the talk is, what's next? I guess there is a lot on your plate in terms of numerical modeling, but I imagine that after this extensive experimental campaign, there might be already plans for investigating the use of it, like in design or more experiments. Or
so the thing that would come up next immediately is really to validate the experimental results and then run a wide parametric study to look at different material properties of the steel, different rubber contents and so on, and then to compare that with existing codal provisions, including Eurocode 4 and maybe some stuff in Eurocode 8 as well. And on a wider scope, I have to write my thesis and and submit sometime in April. So let's see how that goes.
Okay, thank you very much, Mohamed, and thank you all for joining us today in person and online. And I would say another round of applause to.
Thank you very much.
And yeah, you're all invited to join the networking drinks.